Hello everyone, my name is Inga and I'm very happy to be here and to shed some light, perfect, to shed some light on the Llvm Swift compiler. At first I will tell you a little bit about the compiler infrastructure, the compiler architecture, and then we will move on and dig into some low-level stuff that will help us to understand, to debug and to improve our applications in Swift. But our applications in Swift, well, I have to admit that I'm not a Swift developer. I'm coming from the other side. I've been developing a customized version of a compiler, Llvm compiler for C and C++ languages. So something totally different, but the Swift compiler is based on the Llvm compiler, and this is why I'm here today. Okay, I mentioned a few times the word Llvm, this abbreviation, so let me explain what it stands for. Llvm is an abbreviation for the low-level virtual machine. It was a university project which started in 2000, and it turned out to be a huge success. Its main goal was to come up with an utterly new compilation strategy that could support compilation of both static and dynamic compilation of an arbitrary programming language. And they succeeded. So at some point, Apple came to Chris Lattner and invited him to work at the Apple company. So then moving from old GCC to a modern Llvm was just a matter of time. And in 2010, Chris Lattner started to work on a Swift language. And it was supposed to be a language to make the most use of the strengths of Llvm compilers. So normally it is the other way around. You have a concept for a language, you have an idea how to implement something, but you think about the developers mainly, and then you care about the compiler, and then it turns out it's so difficult to optimize. But it was different this time. They had a powerful tool, and they wanted to design a language that will make the most advantage of this tool. So it sounded very promising. What are other strengths of Llvm? Okay, why Llvm was chosen by Apple to be developed, to be supported as the main compiler for Xcode? Well, to be honest, GCC is still better when it comes to producing fast code. When it is about C++ and C applications, if you use GCC, probably it will produce code which runs faster. So what were the reasons to choose Llvm? To its main strengths, one can... this is what happens when I use mic. Okay. So to the main strengths of Llvm compiler, one can count a modular architecture. It means that Llvm compiler is a set of reusable libraries. And it's very easy to modify, to customize the compiler. So you only have to take one brick out and put another one, and then it works as a charm and as you wish. So this is undoubtedly a huge plus and a huge advantage over GCC. GCC is still just a big block of code, and if you just change one itty-bitty thing in the code, then you have a butterfly effect, everything collapses, and it's still a problem when it comes to GCC. And the second strength of Llvm is its intermediate representation. You see, we have code written in Swift, and for an average programmer, an average developer, it is easy to understand. And we have also assembly, which is, okay, if you are desperate to read it, and if you really want to optimize your code, you will read it. But it's time consuming, and it's not human readable, it's rather computer readable. So what Llvm has an intermediate representation, which is somewhere in between. And the most important feature of this representation is that it is independent from the language and independent from the platform, from the architecture. And we will come back to this feature. It will turn out to be really nice. and really useful. Okay, and there are some people who claim, it wasn't because LLVM is a superb compiler, but it's because of money. It's because of the license. GCC was developed under GPL license, so it is a copyleft license. It doesn't allow you to derive commercial products that contain GCC code. And when it comes to LLVM, LLVM has less restrictions, so you can develop and commercialize products that contain LLVM code. So, but whatever the reason, it might be the money, it's Apple after all. So, but whatever, now we can enjoy a wonderful compiler architecture. So let's have a look. At first, let me begin with Clang compilation process. We start with our source code, and what happens to our source code, what happens to our lines of our code that we wrote when we pass it to a compiler. So at first we pass it to a module which is called a parse module. It checks if the syntax is okay, and it produces as an output AST, which is abstract syntax tree. Basically, it is your code, but it is nicely structured as a tree. So it is easier for a compiler to do some other optimizations, and it's easier for the compiler. And next you move on with your code to a semantics module, when you check types of variables and whether a function returns the correct type and so on. And in this module we also add some annotations for AST. And then what is interesting is that we move on to the module which is called IR generator. And this module is responsible for turning our source code into intermediary representation, into IR. So as soon as we have this representation, we can ask the compiler to optimize our code, and then we get our optimized IR that we can pass to the backend. And what is really nice is that if you want to modify the compiler, if, for example, you want to produce code for a different architecture, it is enough to change the backend, to switch the backend. You do not have to rewrite the whole compiler, but you only change the part that is dependent on the architecture. And the same when it comes to the language. If you would like to implement your own compiler for your own language, the only thing that you have to do is to rewrite 3 modules: parse module, semantics module, and IR generator. And as soon as you have IR, a representation which is independent from the language that you use, you can rely on LLVM, and LLVM will take IR and will optimize it and then pass it to the backend, which produces the machine code, which is understandable by the machine. So it looks like something that should be very easy. It is easy to modify the compiler. Well, as if you know how to write these 3 modules, it is. But was it enough in the case of Swift? Well, the problem is that the IR representation, this intermediate representation, is too low level. It is enough for languages like C or C++, but Swift is a high-level language, and it contains 2 high-level abstractions to be represented by IR. If we left the compiler solely with the intermediate representation, then it would lose information about abstractions, and it wouldn't optimize it well. Okay, so it wasn't possible to just have this intermediate representation. The compiler wouldn't optimize the code well. It will lose high-level information. It was necessary to introduce another layer of abstraction, something in between, something that is a little bit lower level than the Swift itself, but it still contains high-level information so that the optimizer can then understand that, hey, here we have a dictionary, we have an array, and we can optimize these high-level abstractions. We couldn't do so with intermediate representation. So what we have here is now CIL generator. CIL is Swift intermediate language, and this language allows us to represent code written in Swift so that the compiler can understand and retrieve some information and optimize it. And this seal that we have when we pass our source code to seal generator is raw seal. It still contains some data flow errors and it is not diagnosed seal, but then we can move on to optimization passes and to diagnostic passes, and then we get canonical seal. And this is great news for us, because what we can do is we can retrieve information about raw seal, and then we can retrieve information on canonical seal, and we can observe how our code was transformed, which optimizations were applied. We can observe changes in our code and adjust it so that it is better and it is much more efficient. Yes, the only thing that we have to do is we have to know how to understand seal. So now that you know a little bit about architecture, I would like us to move on and to finally learn how to read seal, of course. So at first, let me put here some commands that you can put in your command line to get seal from your application, from the code. These commands are valid for Linux operating system because this is the one I'm using, but there are counterparts, there are analogs for Mac OS, so you can just Google them and try it on your computers. The first command produces the raw seal, which is not optimized, and the second one gives us as an output seal which was optimized by the compiler. And then we can compare them and find out what has happened to our code. At first, when we open the file with our generated seal, it may be surprising that it's not as human readable as we thought, because we can find such a name for our function. But it is because the compiler has to mangle names of functions, because each function for a compiler has to have a unique name. Sometimes we do overloading, sometimes functions have the same name, but they need different parameters in our code, and the compiler takes this information and creates such a monstrous name for our function. But we don't have to look at these monstrous names. We can use the tool which is called Swift demangle, and then our file with Swift intermediate language contains such nice and human readable function names. Okay, now we are ready to have a look at the generated file. Of course, the file that is generated by the compiler with seal representation is still too large to be presented just on the one slide, so I put some chunks of most important chunks of this file so that later you can understand what's going on. At the very beginning of the file, we can see that there are some libraries imported. The first one is a built-in library, which is an interface between Swift, between seal and Llvm, and the second one is something that connects seal with the Swift library. So these two libraries here. This is the interface for these two libraries, one could say. Okay, so let's move on to the next chunk of the code, and here we can see a declaration of a global variable. The comment that is above was not added by me, it was added by a compiler, so really the information that you get is very useful and allows you to understand what is going on even before preparation, even without preparations. So here we have a global variable. It is annotated as a seal global. It has visibility hidden. It means that it's only visible within the module. It is not public or private. And then we can see the name of the global variable. It is just foo. And the type of the variable, and it is int. This type comes from the library, the Swift library. It is still a high-level type. And underneath, what we have then? Then we have main function, which definition resembles the main function that we know from C languages. It is it is exactly the same. Have a look at the parameters, it takes integer, so it's the count of arguments, and the second parameter that it takes is the number of is the pointer to character. So it is exactly the same as what we have in C language, and this was generated automatically by the compiler. Also, of course it returns the integer. Okay, and what we have inside this main function. This main function wraps the top code that is placed in your file, and it consists of basic blocks, as every function in C. These basic blocks are annotated here as BB0 and BB1. Okay? And now we will try to understand what is inside these basic blocks and what the instructions look like. Okay, so let me move on to a simple example. Here we have a function foo, which takes as an argument an integer. It also returns an integer type, integer value. In the first line, it allocates a variable b and assigns a 0 to this variable. Then we have a while loop, which checks if b is less than a. If so, then increments b by the value of 5, and then returns b. So what would C look like for such code? So the first line in this function is the basic block BB0. Okay, and now let's have a look. In the first line, we allocate space on the stack for the variable b. It is all written within this line. So we use instruction alloc stack, which allocates space for integer, and it returns the address to the space to the memory on the stack. So variable %1, it is a variable. It contains address to the value of variable b. Okay, these numbers %1, %2, %3. These are names for variables in C. And maybe you will notice a special thing about them. It is that each of these variables is assigned a value only once. And this is on purpose. This is called an CCA form, and it also allows for optimizations, for to optimize the code easily. Okay, so the variable %1, the variable number 1, has the address to the variable b. And then we move on to next 3 lines. And these 3 lines serve to create number 0 and to store number 0 in variable b. We can see at the very beginning, in the first line, among these 3, the instruction integer literal, which creates an integer of the given type. As you can see here, we relate to the library that was imported, the built-in library. So this type int64 is the lower type. In Swift, we would have just the int, but in C, we can translate Swift int to built-in int64. So this is the place where it happens. This is the place where the compiler knows that when we put int in our code, we meant int that has 64 bits. And then we tell the compiler, well, the compiler produced the number that is the value of such an integer. So it's 0, it's just 0. And the variable number 3 stores the created integer value. And then we move on to the next line. And in this next line, what is the main instruction? It's struct. This instruction creates a structure. This is a structure of int type. So this comes from the Swift library, and the structure contains this row int64 type. The value again is stored in the variable number 4. So what we can see, what is the conclusion, is that Swift has its types, keeps its types as structures, and these structures are simply wrappers over some low-level types. Okay, this is the conclusion for us. And the third line stores the value that was just created, so the value 0 in the place that we reserved for the variable b. And the type, okay, here we have also the type of the variable number 1, and it is just the pointer to int. As I said, variable number 1 keeps the address to the variable b, which is of int type. The next instruction redirects us to the next basic block, which is bb1. Okay, so I also put it on our control flow graph to the right, so that we can see how the program looks like in terms of control flow graph. And the basic block number 1 is the header of our loop. So it should compare two integers and then check if the first one is less than the second one. And the code we have below. So let me analyze it. At first, what we do is we retrieve the value of b. You remember that %1 was the place where we kept b variable, right? So we load the value. So now the %7 is equal to 0. Then in the next line, what we do is it's not equal to 0, but it has the structure that we created, and the structure is a wrapper over 0. So what we do in the second line is that we retrieve the value. We retrieve the value from the structure. And in the third line, we again retrieve the value, but the one that was given as a parameter to our function, because number 0 is the parameter that was given. Okay, the next line contains an instruction which compares two values. As you can see, its name is, well, CMP CLT int 64. So it compares values which are integers 64 bits. It takes these two values that we have already retrieved as parameters, and it returns the type that is built in int 1. So it's just a single bit. It can be set to 0 or 1. Then we check the condition. After we created a Boolean value, we simply check if these two numbers were in this relation, so b was less than a. And if so, we go to the block bb2. If not, then we should go to the block bb3. So the first case is that b is less than a, and we should go to the block bb2. Here, what is happening here is, as the first instruction, we add two integers, and the result is the value is the integer that is the sum of these two integers, and also one bit. And this bit is because we want to check if there was an overflow. If we compile our code with a dangerous flag O unchecked, then it doesn't have this special bit, and it doesn't check whether there was an overflow or not. But here it was compiled with a flag O none, so without optimizations. So we check for each operation, for each arithmetic operation, we check whether there was an overflow or not. And this happens here. Here we extract the result of the operation, which added our two numbers. You can see that number 20 have the information about the overflow. And here we have the instruction conditional failure. So if there was an overflow, then the code crashes right here. Informs us about the situation in this place. Then what we can do next is we can assign the new value to b. So this is what not assign a new value to b, but we can simply retrieve. Yes, we can assign the value to b. I just realized I haven't mentioned where is our 5, and it was number 14, so I apologize for this. In this operation, when we added 2 numbers, number 16 was B and number 14 was 5, but I haven't put it on the slide because it produced a very large block of code, and I didn't want us to be bored to death. Yes, and after we increase the value of B by 5, we can go back and check again the condition, whether B is less than A. So we go again to the block BB1, okay? Is that clear? I hope so. And what happens if B is greater than A? Then we go to the block to the basic block BB3, and what we do is we retrieve the value of B. You remember that we have B in that we have a pointer to the structure with B in variable number 1. We deallocate the memory on the stack and return the result. So it was much easier. Okay, so I hope this example gave you some taste of what is SEAL. I don't know whether it was clear, so if you have some questions, and maybe, I don't want you to write code in SEAL on your own. I simply wanted you to have a taste and to learn how to retrieve some information, because, well, probably you won't be generating code in SEAL, what for, but you might need to analyze this code. So it is a good thing to know how to understand the code that is in this representation. So this is the main goal, so don't be afraid. If you are confused, this is the right first impression to have. So, but yeah, I assure you that later we will understand and we'll have some intuition what is behind these instructions, gibberish instructions. So just have some patience, and yeah, it's worth it. Okay, so now that we know SEAL, we can use our knowledge in order to check if we understand what is backstage, what is happening behind the curtain with our code. So we can talk about optimizations. We have 3 flags currently in the Swift compiler. The first one is none, and this is the flag that tells the compiler, please do not optimize my code aggressively, just apply some basic optimizations, some diagnostic passes, but nothing above it. And it is good for development when you want to have full debug information, because when you apply the second flag, which is the flag minus big O, then you lose some debug information, but your code is optimized. So this is the right flag to be chosen for the production code. And there is also the third flag, unchecked. As I mentioned, this flag, for example, tells the compiler, do not check if there are some overflows. And probably you don't want to use it unless you work on high performance code and you are sure that the input is all right and nothing bad will happen. So almost never, because you cannot be sure. Okay, so let's have a look at these basic and guaranteed optimizations. So these optimizations are obligatory, and no matter if you have the flag big O or not, these passes just have to be applied to your code. Your code will be modified in this way. And here I enumerated some of the optimizations I would like to talk about. At first, I don't want to analyze SEAL right now. You are a little bit tired after this introduction. So I will begin with something easier, something very basic, just to recall that the first optimization that is performed is mandatory inlining, and probably we all know what is inlining. If you have a function do stuff which is very simple and it just takes 2 integers and returns the absolute value of the difference, then probably you would like this function to be inlined. So when you use the function, like here to the right, you call the function to assign the value to the variable c. you would like the compiler probably just to copy the code, so you don't have this overhead that is related with calling the function and returning from the function. It's a lot of things to do for the processor, so we would like to avoid it. We don't want such overhead. And then it is very nice if the code is just imported and inlined. But on the other hand, it makes the size of your binary bigger, so it also can make your code slower, and sometimes you have restrictions when it comes to the size of the binary, so you need to consider whether it is good for you or not. And you can tell the compiler if you want it to inline some functions or not. You have some keywords, you probably know all of them, or maybe you haven't heard about transparent. Have you heard about transparent keyword? Anyone? Okay, so it's as I thought, it's not too popular. So you have the keyword to decorate your function inline always, and it tells the compiler, please inline this function. I know it is good for my code, no matter what your diagnostic passes say. I want this function to be inlined, and the compiler will inline the function unless you don't call it too many times. If you call the function too many times, then the compiler knows that the size of the binary will be just too big and it won't inline the function. And you have also the keyword inline never to tell the compiler, oh, I know you might want to inline the function because it seems to improve the performance, but I don't want the size of my binary to be bigger, so please don't do this. And then you use the keyword. But also there is one keyword that is, as I said, well, maybe not very well known. It's the keyword transparent, and it tells the compiler to inline the function no matter what. And also it asks the compiler to do this at the very beginning, so it puts the code in various places and then runs all other optimizations with the function inlined, and this might have a huge impact on your application. So you can try to put this transparent keyword or not. Some people claim that it is better to rely on the compiler and to trust the compiler that it knows when to inline the function or not. Okay, so now let's move on to the next optimization. It's constant propagation. It's also probably very well known, and it's simple. When we have such a easy example, a simple example, we have a function add, which just adds two numbers, and we have a function calculate, which refers to the function add, and it also introduces some constants. So we would like the compiler not to allocate space, not to do this all assignments, because it has constants to operate on. It can just calculate it in the compilation time, not in the runtime. Okay, so at first, what the compiler do is, let's focus on these 3 lines. So if we have constant propagation in the compiler, then the compiler doesn't even create the variable b, because it understands that b is just an argument for the function add. So we just create the value 2, not the variable. And also, we pass as an argument not variable a, but just simply its value, and we have already the value calculated and assigned to a in the 3rd line. And if we did inlining prior to constant propagation, then it looks even better, because the function add has been already inlined in the code. So the compiler can perform computations, can just do these arithmetic operations in the compilation time. And then after applying O flag, all these unnecessary constants disappear, and simply we have the value returned. So it's a very nice optimization. It's basic and it's obligatory. It's performed also for the 2nd time. So it's good to know that we have something like this. And now something more advanced, and here we will make use of our knowledge of seal. Okay, Okay, so I would like to tell you about the optimization which is called memory promotion or capture promotion. What does it mean to promote memory? Why do we have to care about it? Well, we have two types of the memory basically in our application. We have the memory allocated on the heap and memory allocated on the stack. And for some reasons, I will quickly recall them to you. We would like to allocate memory on the stack. It's simply more efficient. And let me explain to you shortly why it is more efficient for us to allocate memory on the stack whenever we can. Okay, so the stack is a contiguous area of a memory, and it's used for storage of local variables and for passing arguments to functions, unless there is no free registers, of course. Okay, and underneath we have a simplified example to analyze. So let's assume we have a variable c, and when we have such an instruction, the compiler simply allocates some memory on the stack, and the stack pointer moves. So now we know that the free memory available is underneath c, okay, below c. Okay, and then the next instruction, we have a variable d. Again, we allocated memory on the stack and variable e. So as you can see, allocating memory on the stack consists simply in decrementing the stack pointer. Stack pointer points to the address which is available memory right now. If we want to allocate memory, we simply change the address that the stack pointer points to. Okay? It's that simple. But when we have allocation on the heap, it's slightly more complicated. Because the heap is typically used for the creation of dynamic data objects. That's the first information. And the second one is that it requires management. For example, in case of Swift, it's of course reference counting. We'll see how it works. Okay, another simple example. We create object wrapper. So the object itself is in the heap memory, but the pointer to this memory, the variable that keeps the address, the reference, is on the stack. Okay, and also the number 1 means that there is one reference to this object, and this is something that probably we all know. Okay, and another object d is also created on the heap. Then we make an assignment, so we assign the same object to another variable. We have 3 variables on the stack and 2 objects allocated on the heap. And we also want to return the value e, and this makes another reference. This increases the number of references to the object, to the second wrapper object. And now what happens when we leave the function is, of course, we pop values of stack variables, so we don't have e anymore, so the counter is decreased. Again and again, we can get rid of the first object. This memory can be freed, and we are left with the heap memory with only one object and with the free memory behind the wrapper and in the front of the wrapper, or above and below. Yes, so the memory is now fragmented, and we need to remember where we have some free memory on the heap. It requires additional work. It's additional overhead. Okay, and the second thing that we need to keep in mind is that memory that is on the stack is limited to one thread in application. And when we have to do with the heap memory, then it is shared by multiple threads, so we also need to care about thread safety. So it's another disadvantage. Okay, so to make the story short, we want to, so the cost of heap allocation is bigger than the cost of stack allocation most of the time. So we would like to allocate things on the stack. Okay, so maybe we should just avoid classes and we should just stick to value types. Well, the problem is that not only objects are allocated on the heap in the Swift, but also arrays, dictionaries, and strings and other value types, they allocate memory underneath. And there is also another abstraction that uses the heap memory, and this is closure. Okay? And Why is it so? Well, have a look at this example. We have a function bar. We allocate memory for one variable, assign a value 40 to this variable, then we modify it somehow, and create closure that will be returned. So we cannot allocate this variable x on the stack, because after we return from the function, the memory that was allocated on the stack for this function is not valid anymore. Okay? We moved the stack pointer. So the variable x cannot be on the stack, it has to be on the heap. And it produces additional cost. But when we look at this example, we can also notice that, hey, this variable x, it is not modified after we create the closure. We do nothing to the variable. So couldn't we just pass this variable by value, not by reference? Okay, so that it's not a context, but it's just a value. Okay, so yes, we can do this. If there are two conditions that are met, we can pass variables by value to a closure. The first condition is that the variable is not modified after we created the closure, and the second condition is that we do not change the value of the variable inside the closure. So it's like in this example, we only read the value of x and we do not modify it after we created the closure. The compiler knows about it and it wants to make the code optimal. So now we can find out what happens underneath. I'll just show the slides quickly. So but if there's something that you would like to ask about, just please ask a question and I will address it and I'll try to explain. So now, at first, let's consider the situation that we have without optimization. Okay? So this is the row seal that we are now looking at. It's without optimizations. What happens here? At first, we want to allocate memory for x variable. So what we do is we use instructions alloc box, which in this instruction allocates memory on the heap. Then we retrieve the address of the variable with instruction project box and store the value. Number 5 is 40, and in the last line we just store this value in the variable. Okay, what we do next? We modify x. So we find the reference to the function modify, and then we apply this function to our argument number 1. Okay? It's just, you don't have to parse the whole line. It's just it's important to know what's going on, but you don't have to understand all the details. Okay. What is next? We create the closure, which is not written here. And then, because the code is in a different place, but what we do here is we partially apply the argument to our closure. We can see that here we have this partial apply instruction. Earlier, before we partial applied our argument, we did something like strong retain. And strong retain and strong release refer to reference counting. So also these are additional operations we would like to avoid. And then we return the closure. The closure itself has to, again, retrieve the address, load the value, and then decrement the counter of the variable. So there were some instructions we would like to avoid. We had to strong release and strong retain. We have to load the value and do a lot of things which are maybe unnecessary. But with the optimization, we don't have to do this. We don't have this overhead. So now let's have a look at the code, which is canonical seal, which is the code with applied optimization. We allocate memory on the stack for our variable. We don't have to have this alloc box. Then we store the value 40. It's very simple. We also apply the function modify, just as before, and then we do partial apply, and we pass as an argument not alloc box, not the reference to the code which was allocated on the heap, but the value. So we pass the argument by the value, and the closure is simple as that, instead of our 3 lines that we had earlier. Okay, so this is done by the compiler, and we do not have to know about it. Well, it's good to know, but it's very optimistic to know that the compiler performs such optimizations. But I wanted to tell you about this. Okay, yes, another slide. In this example, which was modified, which was optimized, we didn't need to decrement the reference counter, and the function modify also could be inlined, and then everything is very simple. But I wanted to show you this example because there is one thing that we can do to stop the compiler from optimizing this code, and it is enough to put the modification after we call the closure. But when it comes to the result that is returned by this function, when it comes to the meaning of this function, of this code, it is exactly the same. But now we don't have this assumption. The compiler knows that the variable x will be modified, and it won't optimize the code in such a way as it was before. So just a single thing, such a simple thing to spoil all these suburb optimizations. So this is why we should know about these things. And just a quick example to show you the numbers. So we have a function modify which takes 3 variables. I added 2 additional variables to make it more to make the example, to make the numbers bigger, so that it will be that the optimization will be much more visible. And we have the same function as before, but it operates on 2 additional variables. And in the first example, we modify variables before we call the closure. In the second one, we modify them afterwards, okay, as you can see. And then we do this a huge number of times. And what are the results? If we compile the code with the flag O_none, then the second example is 3 times slower. If we apply the flag that optimizes the code further, then we can see that the difference is just enormous. Because, well, in the first example, the code could be inlined and probably it was just a constant. Afterwards, in the second one, it was impossible because we wanted to modify variables afterwards. Okay, so in such a way, we lost such an optimization. Okay, now I told you about some guaranteed optimization passes. There are other guaranteed optimization passes. They check if you return correct value of the correct type. They check if everything is initialized. And there are also some high-level optimizations which are related to classes, to protocols, to generics. And I wanted to tell you about all of them, but I learned that I cannot run out of time. So, but yes, I foreseen such. I have thought about it, so I have such a button here, not to go to the next slide, but to skip some slides. So let's click on it. Yeah. Oh, it works. It was just one of the examples. I simply want to tell you the conclusion because I promised you to give you some tips on how to optimize the code. And okay, so I'll just quickly tell you that I will put the slides on the website so that you can analyze, you can see the seal code generated, you can learn how to read seal, and you can find the reasons for which some optimizations just don't work if you modify your code a little bit. So just the conclusion. Here I wanted to show you why you should put private keywords. And you probably know that you should whenever it is necessary, or to put final keyword. It is also very useful to improve your code, and you can find on the skip slides why and how it is written in the seal. And also generic specialization is the same. And the conclusion was that it's just a conclusion, is that you should provide the compiler with as much information as you can. And if the compiler cannot create a specialized version of your method, then you should tell the compiler in a straightforward way, specialize this method. And you can use the keyword specialize, which I think is also not very well known. I found it in the documentation, but probably some of you don't know about this keyword. Performance inlining, I had a great example and I wanted to teach you how not to be disappointed, but I think it's just maybe stuff that I will tell you about maybe during next presentation, who knows, because it will take me quite a lot of time. So of course this is a good hint for the future that you should benchmark everything, and if you can allow overflows, it will really speed up your code. If you have any questions, send me an email. And I suppose that some of you expected that I will tell you how to train your LLVM Dragon. It's not an accident. It's not by an accident that the logo of LLVM compiler is a dragon, such a powerful dragon. And the answer is that you don't have to train your compiler well, because it has been already trained well. All you have to do is to treat it well. So please don't impede actions of the compiler. You should, well, probably you do so, but just to recall you that it's good to know, it's good to learn, to find out how things are implemented and what is the abstraction underneath, what is this lower code representation, just to know what you cannot do, so to allow the compiler to optimize your code. Yeah, so, but you know, it's a great thing to write code in Swift, because in C++ you just have to do a lot of things to optimize your solutions, and here you just, please don't do things, and the compiler will optimize everything for you. So this is the difference, and I'm very glad I got this motivation to find out more about Swift, so thank you a lot.